So, thank you very much for coming for today's Colloquium. Today we are very much excited and very fortunate to have Professor Sachdev from Harvard. He's one of the most prominent theorists in our age, theory. And I think he started undergraduate in ITT Berry, and then he moved to, but in undergraduate, he moved to MIT and finished undergraduate there, and then he went to Harvard and worked with in the PhD work with David Nelson, and then to the time I think around the ITC and things flourishing. So he went to Belarus for a few years, and then he became a faculty at Yale, and he was at Yale for 14 years, and
18.
18. I'm sorry, and this Sachdev-Ye paper was produced in Yale, and then 2005 he moved to Harvard University, and so he's a professor at Harvard University, and he has of course many honors, including the Onsaga Prize and Dirac Medal, and many others that you can find on his website. So he worked on many things of correlated electron systems like unconventional superconductors, spin liquids, and also probably he has some work connected to the string theory, and he published 3 very well-known books, Quantum Phase of Matter, and the others. So let me stop here and ask Sudhir to give a talk about entanglement in quantum matter, spin liquids, and Sachdev-Ye-Kitaev model.
Okay. Thank you very much, Tomo, for the kind introduction and the invitation to be here at Columbia. I'm returning after many years, and it's great to see all the changes and all the exciting things going on here. All right, so this is meant to be a relatively general talk, but I'll try to focus on recent work, both experiment and theory, and try to give you a flavor of many things that are going on. But as Tomo mentioned, a lot of this work was motivated by the high temperature superconductors, yttrium, barium, copper oxide being the most prominent of those. And if you take a little piece of YBCO, as we call it, and put it in liquid nitrogen, well, it can do an amazing thing like this, where due to the expulsion of magnetic flux in a superconductor, you can get it to levitate and do fun things like that. And this is the kind of experiment you can now do in an ordinary classroom, which was impossible before. And there still is no other material where you could do something like this. It's still the material of choice if you want a good superconductor at some reasonable temperature. Just briefly, I'll mention that one of the most exciting possibilities for the future is the use of these magnets, YBCO magnets, for fusion energy. So this is from the website of a company in the Boston area, which is using YBCO wire, that's what this is, to contain a plasma in a more efficient manner. And okay, well, this is something from their website, so I don't know whether to believe it or not, but I think it's fair to say that these YBCO magnets have transformed fusion research and into quite a different direction. All right, so if this actually works out, you know, that all the effort spent in the 30+ years since the discovery would be worth it. It's still worth it on its own, intellectual reasons, but maybe even for practical reasons. All right, so let me say a bit more about the phase diagram of these materials. So here on the horizontal axis, you have doping, which is just the density of electrons on a single layer of copper and oxygen. It's controlled by changing the oxygen in concentration. And the vertical axis is temperature. So there's many things going on here. In fact, this is a highly simplified phase diagram. Part of the reason it's taken 30+ years to make progress. I'm going to focus on the phases above this temperature Tc, which is the critical temperature for superconductivity, which you can see is as high as 100 Kelvin or 90 Kelvin in this material. So let's look at the different phases here above TC. Oh, before I get to that, sorry. At zero doping, which is the simplest limit, which is now well understood, it's an excellent approximation to just think of this material as just a bunch of copper atoms on a square lattice. Even simpler, you can imagine there's just one electron and one orbital on each copper atom that's active. Now, electron has a spin, and so what happens in this region called AF insulator is that the spins polarize in this antiferromagnetic configuration, sometimes called nail order, where half the spins on, it's like a chessboard, where the black squares are down and the white squares are up. So this is an insulator where the spins polarize in this manner, and this is certainly well understood. The other limit, that's on one side of the superconductor. The other limit that's well understood is if you go beyond the point where there's any superconductivity at high doping. And there you get an ordinary metal, meaning it's not so different from copper or gold or silver. So these are all ordinary metals, extremely well understood. And in some sense, their theory goes back to the work of Sommerfeld about 100 years ago, soon after the discovery of quantum mechanics. Sommerfeld proposed that you could think of metals as just nearly free electrons. And the most important thing was the exclusion principle that fermions obey, which was only discovered in 1926. That could then lead to a resolution of many open problems in what was then known in the theory of metals. And that theory has been developed a great deal. And by 1980s, when these materials were discovered, its most advanced forms were agreeing extremely well with many, many experiments, really the foundation of solid-state physics. So one of the main features of this theory is something we call the Fermi surface. So this is the boundary between the single particle states that are occupied and empty. So in a clean crystals, you can label the states by momentum. And so this is a measurement through a photo emission experiment of this boundary. So there's this boundary here between the occupied states, which are actually inside, and the empty states, which are outside of the electrons. So subsequently, so this was the Sommerfeld model of nearly free electrons. A very deep theorem due to Luttinger, in fact, here at Columbia, was the following, that even if after you put in interactions between the fermions, the shape of this Fermi surface would change, but its area could not. The area enclosed in this region should be independent of essentially everything other than the density of electrons. Once you know the density of electrons, you can deduce what must be the area enclosed by the Fermi surface. So this very deep theorem, again, is the foundation of solid-state physics. And if you apply it here, you find it works beautifully. That in fact, even though these are very strongly interacting electrons, you measure the area enclosed by the Fermi surface, you find it's exactly the free electron value. So that's great. That seems to work. Then you can ask, well, what about the superconductivity? Well, we do have a theory of superconductivity due to Barty and Cooper and Schrieffer in 57, which said that you start with one of these Sommerfeld metals, and then you put in some weak attraction between the electrons near the Fermi surface, and that will give you a superconductor. Now, in the ordinary superconductors, the old superconductors, that attraction is due to phonons. But here there were already suggestions, even before the discovery of these materials, that the spin fluctuation, the antiferromagnetic spin fluctuations, could induce superconductivity via an attraction on the Fermi surface in a higher angular momentum channel. And that also, it seems, worked out in the end, although quantitatively not accurate. You could start from this kind of metal and really get the right type of superconductivity, the so-called D-wave superconductivity that's actually observed. So that's, a very strong success for theory. Okay, but what about as you move to the left where the TC is really highest? Now, if this picture of this kind of picture held through the entire phase diagram, well, then I wouldn't be standing here. The problem would have been solved. But that's not what happens. So what you find quite remarkably is that the metals you see above Tc at lower doping are nothing like Sommerfeld's metal. Most dramatically, that happens in what's called the pseudogap. I'm going to say a bit more about this as I go along. And the modern understanding is that you really need a drastic modification of Sommerfeld's theory, and as formalized by Landau a bit later. And you need to include, in a fundamental way, many particle entanglement. So that's really what my talk is about, how many particle entanglement modifies the properties of materials. And in particular, one domain where we understand many particle entanglement extremely well today, after 30 plus years of work, is in what's called a spin liquid. I'll give you examples of that soon. And the hypothesis we particularly have been working on, that the pseudogap metal has, in fact, the type of entanglement that you see in a spin liquid. So I'll explain what I mean shortly. And then finally, in the middle, there's a strange metal, which is different from either the pseudogap or the ordinary metals. And it has a different pattern of entanglement. It's not like a spin liquid, which is more characteristic of entanglement in an insulator. It's really entanglement in a complicated metal. We don't have a complete theory of this yet, or even the pseudogap, but the ideas I'll present is that we can learn a lot about what's going on in the strange metal by looking at simpler models, in particular the SYK model. All right, so that's kind of the overview of the problems I want to address. And one of the, these problems are already around in the early 90s, when many of us got involved in thinking about this. And one of the remarkable things and very rewarding things is that the ideas that were generated from this field have had a wide effect on many other fields, including the study of black holes and quantum information theory, quantum error correction, and I'll give you some flavor of that too. Okay, so let's first talk about entanglement in the very simplest case I'm calling this entanglement of stationary electrons, meaning they're insulators. They're not actually moving around. What's changing is the way their spin is entangled. Okay, but to go back, what is the origin of entanglement? In some way, you can think of this as really discovered in 1865, where Kekule was thinking about the structure of benzene as a chemist. This is before quantum mechanics, which was invented in 1925. And the puzzle there was chemists knew about valence bonds and single bonds and double bonds. So if you had 6 carbon atoms in benzene and available one extra double bond for each atom, well, then they could only form a double bond in either this way or this way. Oops. There are 2 possible configurations where each ellipse represents a valence bond. In some limit, you can think of the valence bond as what you call an EPR pair, where you have one electron that's up and the other electron's down. This is the ground state of a spin dot S1 dot S2 Hamiltonian that you learn about in undergraduate quantum mechanics. So these spins form a singlet. So in each such valence bond, 2 electrons are entangled in this EPR pair. But Kekule's proposal was that, in fact, there's a resonance between 2 different configurations, and the actual state today we would write down as a superposition of these 2 configurations. So now you have entanglement of 6 electrons, not just 2. And the virtue of this state is that graphene would remain a perfect hexagon. If it was either this state or that state, it would distort into a non-hexagonal shape. And that didn't seem acceptable. Of course, today we know it is a perfect hexagon. And this is how you think of it. All right, so that's simple enough. But the question is, you've gone from 2 to 6. Can you go from 2 to infinity? So one very interesting place to look for that is in what's called the triangular lattice antiferromagnet, where unlike the square lattice that was present in the copper oxide material, we put the spins on a triangular lattice. So there are spins on each side of the triangular lattice. These are spin a half, two states up and down, as shown over here. And they interact by this Hamiltonian S1 dot S2 for nearest neighbors, say. Now, for the nearest neighbor model, we know today that the ground state is very similar to that in the square lattice. It's not quite a checkerboard arrangement. It's this triangular lattice non-collinear arrangement, which is the configuration you would write down if we just thought of these spins as classical vectors. If these were classical unit length vectors and you want to minimize this energy, well, you want near neighbors to point in opposite directions. Well, you can't quite do that on a triangular lattice. So you make this compromise where they make an angle of 120 degrees with each other. And that's the global minimum of the classical system. What we know after a lot of numerical work is that is also the ground state, even for the spin a half system, for the case of the nearest neighbor model. But way back in 1974, Phil Anderson made a radical suggestion that in fact, perhaps the ground state of the triangle lattice antiferromagnet or related models could be what we now call a resonating valence bond state or a spin liquid, where the idea is very similar to Kekulé's idea for benzene. Here, if you just had, if you just took this Hamiltonian for two spins, these two spins say, and you look for its ground state, well, the ground state for that, is this singlet, which is the same thing we saw in benzene. So that's a possible singlet. And similarly, then you can pair up each electron with its partner to form this particular dimer covering, as we call it, of the triangular lattice. And Anderson postulated that perhaps there could be a ground state where you have a sum over all possible dimer coverings. So now, unlike Kekulé, where there were only two possible dimer coverings, here there's an exponentially large number of dimer coverings. Even for a lattice of size 20 by 20, the number of coverings of order e to the 400 or something like that. So it's huge. And so this is really a gigantic sum. It's e to the 10 to the 23. That's how many terms are there. And these coefficients presumably are determined by some complicated microscopic parameters. All right, so that was just a postulate in 1974, didn't get much attention in those days, that the sum of all these dimer coverings, here's another picture of them, huge number, form a macroscopically entangled state. All right, so today, of course, we understand that the structure of such states much, much better. And there's been this remarkable development in theory in classifying and understanding the structure of such states. There are many different states, and we can now put them in different categories and understand something about their excitations and many other strange properties. So if I want to put my finger on what's really new about these states, these were the first such state where it had this remarkable property. What's really new about it is the following, which sometimes you can loosely call a fractionalization, which is that if you look at the excitations, this is the ground state, fine, it's very complicated. If you look at now some low-lying excitation of this ground state, it's a fractionalized excitation, meaning that there's no local operator. There's nothing you can do locally to create one such excitation. So it's kind of immune to all local operators, but it's still there in the sample. And so in fact, the best you can do is create two of them. You can certainly, there's usually no obstruction to creating two of them. And then you would have to separate them far away. So all right. So, and these different excitations that cannot be perturbed by any local operations are sometimes called super selection or anion sectors. So let me just give you a simple example. So if you took this state with the superposition of all of these dimer configurations, and you act on it by a spin flip operator. So a neutron comes in and flips an electron spin, that's a local operator. So initially their spins are opposite. Now you flip a spin and you get two of them. And now you get an excitation that is total spin 1. When you flip a spin, the change in spin is 1. But now you could imagine that what the system would like to do is to separate these infinitely far away. And so here I have then a local excitation. It's a spin a half floating on the background of the ground state. It could not be created on its own, but once it's there, I can forget about this other person. I just have this excitation here, and that's my anion. That's my fractionalized particle, which carries spin a half and charge 0. So in the Sommerfeld theory or Landau's theory, there's no way you could take a metallic state and do anything to it to create an excitation that had spin a half and charge 0. You could create an excitation with spin a half and charge E by adding or removing an electron, but nothing where you didn't change the charge and you got a net spin a half. But here I believe you can. Okay. All right. So that's really what was new about Anderson's idea, that it really gave a whole new type of many particle quantum phase, which had these very novel type of excitations. So this works even in higher dimensions. And today, there's a very fancy mathematical technology for describing all of this, but that's really the key idea. Okay. So way back in 90, we started trying to write down a theory of this. And the way we thought about it was, well, let's start from the state where things are ordered and imagine you add some second neighbor exchange, and then there's a quantum phase transition and you get some kind of spin liquid on the other side. So we developed a theory of the spin liquid, and we're able to say that in addition to having these spin a half excitations, it also had to have a magnetic flux excitation. And that magnetic flux could be pi or 0. And that there was an effective Z2 gauge theory that described the interaction of the magnetic flux excitation and these spin-ons, which actually had an electric charge on the Z2 gauge theory. So this is an example of what we would now call an emergent gauge theory, where you get a theory that's sort of like quantum electrodynamics, but unlike quantum electrodynamics, the way you learn about it, you write down a photon, you write down electrons, and you couple them together. Here, you never write down a photon to begin with, or the analog of a photon here, which is electromagnetism, a U1 gauge force. This is a Z2 gauge force. That's a mathematical difference. But here you write down just the spin Hamiltonian that I've shown you. And once it goes into this fractionalized phase, the way to describe it is by a gauge theory. That's one possible way. Anyway, so of course, this line of thought has come a long way. And a very important step was a solvable model called the toric code by Kitaev. And then people found many other solvable models, and many things have been classified. And there's a whole field of mathematics that looks at all this classification and things I barely know what this means. A unitary modular tensor category, but that's what it is. And this is the simplest example of a unitary modular tensor category. Anyway, so that's been one of the offshoots. And this has been, of course, as you surely know, really crucial, the toric code, in recent work on quantum error correction and superconducting devices. So roughly speaking, the idea of error correction is very much related to the fact that these excitations are immune to local operators. If you had any noise in the system with one spin-on there, it's not going to change the number of spin-on. There's certain properties of that spin-on that are robust. And that's, again, the idea behind quantum error correction. All right, so turn into experiments. So these are very recent experiments in a triangular lattice antiferromagnet. These are the compounds. And if you look at this potassium compound, then this is neutron scattering data over here. And this is some spin-on theory. So the key feature here that I want to emphasize is, so the vertical axis is energy, the horizontal axis is momentum. Now, if you had a regular antiferromagnet, then at each momentum, there'd be some fixed energy for a spin wave excitation. So when you flip a spin, you'll create a spin wave, and that'll have some fixed energy. So you'll see a bright line, telling you the dispersion of the spin wave. And you kind of see that here. There's a bright line. So this particular compound is ordered at 0 temperature, and so that presumably are the spin waves of the ordered state. However, if you look at high energy, you see this diffuse continuum. It seems that you fix a momentum and you go to high energies, there's lots of excitations there, which don't have any fixed energy. Now, that's exactly what the fractionalization picture would say. If you flip a spin and you give it a certain momentum and energy, that gets split into two spin-ons. And now you have to divide the momentum you gave the system in some way between the two spin-ons. And you have to sum over all possibilities. So you get a whole continuum of energy, so-called two spin-on continuum. And so this continuum is in some sense a direct, in principle, a direct manifestation of the defining property of a spin liquid, the correct presence of excitations without any that cannot be created by a local operator. Anyway, so there's some theory based upon the spin-on picture. That's the Schwinger boson theory, and that seems to capture both the continuum and the spin wave in this material. And just very recently, there's been data on the sodium material, which is in fact on the right side. So this would be, if confirmed, the first realization of Anderson's RVB state. And this is still on the archive, but they say that with the gap speed to spin liquid, which is what I've been describing, is the most natural explanation. Anyway, okay. Another different domain in which there have been these kind of Z2 spin liquid correlations seen are in cold atom experiments. I think Tom Manowitz gave a talk about this recently. Not exactly this particular configuration. So you take a bunch of Rydberg atoms, well, rubidium atoms that are trapped by a tweezer. So each one of these circles is an atom. But by laser pumping, you make put some of the atoms in the Rydberg state. So that's the big circles of the atom in the Rydberg state, the small circles of the atoms on this in the ground state. Now these Rydberg states repel each other. So they like to spread themselves out. That's very much like the dimers, which are close packed, but they can't overlap. So there's a very simple mapping, in fact, between the Rydberg states and a dimer covering of the Kagame lattice. And so these big circles form a dimer covering of the Kagame lattice. And there's some evidence from the observations. This is a relatively small system, and there are various issues with equilibration and so on. But they do see some evidence that the ground state has many such configurations. I don't think it's conclusive yet in terms of a Z2 spin liquid, but it's very exciting because here you can now actually measure local observables in a way that you can't in neutron scattering in the other material I showed you. All right, so I told you something about triangle lattice spin liquids and Kagame lattice spin liquids, the simplest ones, how the theory has come a long way and how finally experiments are also starting to see some evidence of such complicated states of matter. So let's go back to the square lattice. And now I want to discuss the pseudogap metal. So what does any of this have to do with the pseudogap? Well, okay, so the pseudogap has a very complicated Fermi surface, and I could spend the rest of my talk talking about our own theories on what this is due to, and many other people have worked on it. But one thing one can say from theory quite confidently is whatever is the resolution of the violation of Luttinger theorem. In other words, can you come up with a theory which gives you a metallic state which does not obey the Luttinger volume? And in fact, you can. And the way you get such things is by imagining that the missing electrons. So if you wish, if you think of these as small pockets, a lot of the electrons that were here have disappeared. So where are the missing electrons? Well, those missing electrons have to be in a spin liquid background. There's essentially a theorem that you can show that works. Of course, it's much harder to compute things in great detail, but that's what we think is happening in the pseudogap metal. And one evidence for these missing electrons is that there should be spin-ons. So do you see spin-ons in the pseudogap? Well, here's some resonant inelastic X-ray scattering data by Steve Hayden's group. Again, I won't go into the details, but if you look in the insulator, you see this beautiful spin wave that you would see, for each momentum, there's a fixed excitation. So the insulator, the antiferromagnet, is perfectly ordered and has exactly what you expect. But when you dope it and you change the density of electrons, you see this big continuum, rather similar to what you saw in potassium YbSe2. And there's really no other reasonable way, in my opinion, of understanding this continuum, except that there's some fractionalization appearing once you dope the system. So I would say this is the best evidence for this, for the hypothesis that the pseudogap metal is associated to spin liquid physics. So what we have been working very hard on is actually computing this kind of data, this kind of spectrum, and comparing to experiments. So that's very much work in progress. But here we have to then ask about square lattice spin liquids. I told you about triangular lattice spin liquids. So what do you do on the square lattice? So a huge effort over the last 30 years has been to take the square lattice Hamiltonian of spin-dot-spin interactions. So this is the Hamiltonian that applies to the cuprates. And then you put a second neighbor exchange J2, which is an exchange here along the diagonals. Now in the real world, J2 is present, but it's rather small. But you keep cranking it up until you lose the nail state that I told you about. And the idea anyway is that maybe this will tell you something about the dope system. When you put in the mobile electrons, how do you lose this magnetic order and get a spin liquid state? Okay, so there's a very long story there. And there's a lot of numerical evidence. This is all data from various numeric analysis. And what's understood there that there is a narrow window over which there is spin liquid behavior. And we are still also trying to understand something about the structure of that spin liquid. It is not the Z2 spin liquid I showed you about. If that had been the case, we would have conquered this problem long ago. It's a much more complicated spin liquid, especially recent work by Yin-Chen He on the fuzzy sphere has told us a lot more about it. Anyway, so I think this is on the right track, though. In this case, we have to think about gauge theories, which have not only spin-ons, but monopoles. And the effect of those monopoles on the physical spectrum is a very difficult problem that we are slowly making progress on. Okay, so that's what I have to say about spin liquids now, and how it's, I think, leading to progress in understanding this enigmatic pseudogap metal. Well, how about the strange metal, which is right in between? So that's what I'm going to turn to now. And here, the key feature I would emphasize is the presence of mobile electrons. The electrons, so far, everything I've been talking about in terms of entanglement doesn't involve electrons actually moving. It just involves the valence bonds moving around. It's something very, very subtle. But suppose you had a good metal, but there was no semblance of any kind of insulator nearby. Could it lead to some other kind of metallic states? Okay, so that's the strange metal. That's what I want to focus on. So what's strange about this metal? Well, first I have to remind you what's an ordinary metal look like. So as I said, it's described by Sommerfeld's theory. In fact, you combine Sommerfeld's theory with an even older theory, which is Boltzmann theory for the classical gas in this room. You combine the two and you get, let's say, the Landau-Boltzmann theory. And that's been the workhorse of everything in solid-state physics. So one of its important predictions is that if in Boltzmann theory, we learned about the collision between oxygen molecules in this room, how that leads to equilibration and increase of entropy and so on and so forth. Similarly, you can ask now in this quantum theory, what is the collision time between these excitations, low energy excitations near the Fermi surface? And the answer is that this time sort of looks like this. It diverges as temperature goes to 0. So it becomes very long as the temperature becomes longer and shorter and shorter, smaller and smaller. And one consequence of this is that the resistance of a metal increases as temperature squared. Okay, now you can ask, now suppose I increase the strength of the interactions, which is U here, then this time becomes shorter and shorter because the collisions become more and more often. And then at some point, this has to break down, or should it? Okay. So if you go through this consistency argument, you find that everything is okay as long as this time is longer than what now people call the Planckian time. This is the time that you would make out of nothing but Planck's constant and temperature. So as long as this time is bigger than this, you're okay. And now you see, the reason for our confidence in this theory. No matter how large U is, all you have to do is make temperature small enough. Eventually, this time, since this diverges of 1 over temperature squared, will become longer than this time, which only diverges of 1 over temperature. So eventually, a low enough temperature, Sommerfeld's theory should be resurrected. Okay. And that really was the case in essentially all the materials that were studied until very prominently in the cuprates it became clear that this simply wasn't true. So what's going on? Yeah, well, that's the second problem we have to address. So here's some data of the optical conductivity. This is measured by shining light at a frequency omega and measuring the reflectivity and the transmittivity or things like that. And from that, you can read off various parameters of the metal, underlying metal. And in fact, here I just focus on this 1 over tau term over here. Now, in Sommerfeld-Boltzmann theory, there's just a constant independent of frequency. But generically, you could, without making any assumptions on the microscopic physics, you can write it as in this form where tau is frequency dependent. So what they find when they measure tau, that it's strongly frequency and temperature dependent in a way that you can't get from a liquid theory. And in particular, it seems to obey this remarkable form. It's just exactly this Planckian time times some function of frequency over temperature. And that's what this is showing you. At high frequency, this tau of omega is linear in omega. But 1 over is of order 1 over omega, sorry. That's this plot here. And at low frequency is 1 over temperature. Okay, so that seems to work rather well, and it's direct contradiction that anything you would get from the traditional theory of metals. All right, this type of data was already there, although not with such precision in the early days. And so we started thinking about this. Is there any model, a toy model that you could write down that had looked anything like this? You have to get around this very strong argument that temperature goes to 0. Eventually, your collision time will become larger than h bar over kt, so everything should be okay. So how could you get around it? All right, so now I'll present a model that does get around it. It's a rather artificial looking model, but I hope to convince you it's taught us a lot. So, okay, this is my spooky dream, which is not true. It's all about snakes everywhere, unlike snakes that Kekulé dreamt of. Anyway, so what is the model? Okay, so you imagine you have a bunch of states. So I label the states by a position, but it could be anything else. These could be orbital labels in a big atom or something. And some of these states are occupied by fermions. So now you want to create a many-body state in which you're going to get around what is it called? So anyway, you're going to get around Sommerfeld-Landau theory, the tyranny of Sommerfeld-Landau theory, and get a state that has a relaxation time, hopefully, which is of order h bar over kt. All right, so what is the model? Well, these fermions are going to tunnel around, and the one restriction you put on them is that they don't move on their own. It's an artificial restriction, but maybe for some reason, if this was a flat band or something, you could realize that in experiment. But for now, we're just playing around to see how you can get around the sum of your lambda constraints. Well, so what you allow now for the fermions to do is to move in pairs. So there's some quantum mechanical amplitude for the electrons on site 11 and 12 to tunnel to sites 5 and 14. So this is some number that you can give me that specifies that amplitude. And so on. So for any such two-body motion, you have some interaction constant determined by all the microscopic details of the system that you can work out. And that's pretty much it. All right, so you can write down such model for n particles. The only trouble is that the Fock space grows exponentially with n. And for n greater than about 30, even today in the best computers, you can solve this problem. You can't even put it on a quantum computer because you have all these fermions moving around, and all quantum computers today are made of bosons. Anyway, so what do you do? Well, so we made the observation in 93 that you make one simple assumption that these numbers are uncorrelated random numbers. That's really the only assumption. Then for n becoming large, you can actually solve this problem. Today, from the help of string theorists, you'll see why string theorists got interested in a few minutes. We know a lot more about the large n limit and exactly how you approach it. And all of that involves some aspects of quantum gravity. I'll give you a flavor of that too. Okay, so but in the large n limit, you can solve this problem with the single assumption that these are uncorrelated random numbers. So what that means is that, except for a measure of set 0, any set of numbers, any model is okay. Because the further thing you can show is that the model is self-averaging. So unlike a spin glass, you have all kinds of random couplings. The actual state of the spin glass depends on every little coupling in the problem. Here it doesn't. As n goes to infinity, it's self-averaging. In fact, it's the champion of self-averaging. There's no other system that self-averages as fast as this. Okay, and the key to that is many particle entanglement. So this is what the wave function looks like. It's a superposition of macroscopically distinct states, just like the resonating valence bond state. But now you actually have fermions, charges moving around. In the RVB state, the fermions were all stationary. It was only the spins that were getting entangled in different ways. Okay, so that's all right. So here's the model if you want to see it in actual terms of creation and annihilation operators. These are independent random numbers. And then you can solve this. And I won't go into the solution. It's not that complicated. You can read reviews of modern physics articles if you want to learn all the details. But let me just tell you what you obtain. So so you obtain, in fact, a model which has no particle-like excitations, no spin-ons, holons, nothing, and no electrons in the low-lying spectrum. It's just each low-lying state is totally different from the other one. So if you had particles in the spectrum, you would say that here you have the ground state, and then you have some other excitation, say a spin-on. The spin-on can't be created by a local operator. But anyway, once you create it, it doesn't look very different from the ground state. It only involves some changes in a little region. Here, every state is totally different from the other one. And the size of Hilbert space is huge. It's e to the n, e to the 10 to the 23. So there's lots of states available for you to have low energy states with. So there's no quasi-particles. And if you imagine taking the system and tilting it somehow and making things flow, you would find that current is not carried by electrons by some entangled quantum soup. Okay, so what are the things you can compute? So one of the things you find, which was already known by 99, and we were extremely excited by this, it has exactly the form that you could write today in this form, where you look at some relaxation time. It's exactly what's seen in the cuprates in the optical conductivity data I showed you. Some function of frequency over temperature with h bar over kt. And the important point is this whole thing is independent of the strength of the interactions, which is also true for the experimental observations, which is kind of remarkable, something you'd never find in the Boltzmann theory. the collision cross-section in Boltzmann depends on the strength of the interaction. That's Fermi's golden rule. U squared is the collision rate. That doesn't happen here. It's totally independent, and it creates this universal structure, which is a direct consequence of this complicated entanglement. Okay, so that got us very excited. But then we found another result, which at least in 2001, kind of discouraged us a great deal. It shouldn't have, but it did. And it had this rather strange property of very carefully stated, an entropy that didn't vanish as temperature went to zero. It has an extensive entropy as temperature went to zero. Now, there are models that were known at that time where you could have this strange feature, which is a clear violation of the third law of thermodynamics, like Pauling's ice model. It was a classical model of some vectors in ice, and there's many different ways of arranging water molecules, but it's consistent with the ice interactions. And so this has some state, many possible state, an exponentially large number of states, with a gap to all excited states. And this would have then an extensive entropy as temperature went to zero. Okay, but this is a very artificial model. You change just one thing in the Hamiltonian, you'll lose this feature. And you get this huge exponential degeneracy. Here, it's very, very different. In fact, this is the first example of a model where you get a zero temperature entropy. Notice I don't say ground state entropy, zero temperature entropy, without any exponential ground state degeneracy. In fact, here's the actual density of states from some numerics. There's nothing, the ground state is like maybe twofold degenerate or something. Excuse me. But I told you about these energy levels being totally different from each other. So if you look at the first state and the next state, they're completely different. But they just happen to have the energies that are exponentially close to each other. So as long as these spacings are exponentially close down to the ground state, you will get a zero temperature entropy, where it's very crucial that you take the thermodynamic limit before you take the zero temperature limit. And this is really the first model to have this property. We could compute this number S naught. That's in this paper. It's hidden in the appendix because we didn't like this result at that time. But it's really the most important thing in that paper. Luckily, we put it in. And then the cinch factor is known today. That comes from quantum gravity, and I'll show you a little bit about that. Okay. We didn't know the cinch factor. Anyway, so Antoine Georges and Olivier Parcolet and I worked on this for a while. Anirvan Sengupta, someone, Chimiao C was interested, but people lost interest in 2001, partly because of this reason. All right. So now what saved the day from my point of view is something I didn't know anything about in 2001, which are black holes. Now, it turns out already in Hawking's theory of black holes from 1976, there was an example of another system which had exactly this feature. As this feature which in the thermodynamic limit, the entropy didn't vanish as temperature went to zero. Okay, so let me say a little bit about that. How am I doing on time? Actually, 10 more minutes, okay. All right, I have to solve the plain metal problem before that. But let me tell you about black holes. All right, so black holes are solutions of Einstein's equation discovered by Schwarzschild. There's a horizon inside which classically nothing from inside can ever escape. And there's a supermassive black hole at the center of every galaxy, including our own. And Einstein's theory actually says that the matter inside a black hole is extremely dense. In fact, it all collapses down to the center to a point singularity, which is why Einstein and many others didn't even believe such things could exist. Today, of course, we know they exist. And to understand what's really going inside a black hole, we have to resolve the singularity by quantum effects. That's very clear. But nobody really knows. I think even today, there's no complete theory for what the structure of the inside of a black hole is. But Hawking made some remarkable progress by not asking what's happening inside a black hole. He asked, can you see some quantum effects when look at a black hole from the outside? And you could paraphrase his argument by imagining you had an EPR pair of entangled electrons, and then you separate them so that one fall inside and the other stays outside. So if you were an outside observer with this one half of an EPR pair in your hand, then since you can't access the inside ever, that EPR, this half in front of you that you have, is completely random. And randomness is entropy, as Boltzmann taught us. And therefore, in this very simple argument, the black holes have both an entropy and a temperature. In fact, Hawking was able to give a precise value of this entropy. And the value, the remarkable things about it, is that it involves various fundamental constants of nature, including Newton's constant, but it's proportional to the area of the black hole. And that you can kind of understand from this entanglement picture, that entropy is due to entanglement across the horizon, because one half of the entangled pair is being lost to you. And so it'll be proportional to the area of the horizon, because that's how many entangled pairs are active. Okay, so, and these are all correct interpretation as we understand today. But this leads to an immediate problem, which you can think of as the contradiction between the two famous gravestones. So this is Boltzmann's gravestone in Vienna, which has a fundamental formula relating the entropy to the density of many-body density of states, D. He wasn't thinking of quantum mechanics, but it's a natural generalization of what he said in quantum mechanics. Yeah, that's why it was K log W rather than D. Okay. Hawking's gravestone in Westminster Abbey doesn't quite have the entropy formula. It has a formula for the temperature. So I wrote the entropy formula here. And so are these two compatible? That is, where does this density of states come from that gives you this entropy? How does it depend on energy? And we know something about how entropy depends on temperature from Hawking's calculation, but can you really get that from a quantum mechanical result? Anyway, so there's of course a huge history of this, especially in string theory. I mentioned that briefly in a minute, but let me mention, what I had the good fortune to stumble upon when I learned about black holes in 2010. So I was learning about black holes, and I first learned that, in fact, was well known that their dynamics is also Planckian. And that is, if you rewrite, you imagine two black holes merge, and they kind of oscillate around for a while, and they settle into a perfect sphere. So there's some damping time, or the quasi-normal mode damping rate. And you can ask, how long is this time? Well, when you express it in terms of the Hawking temperature, it's precisely Planckian. Okay, so that sounded very interesting, suggesting there's some connection between this kind of non-quasi-particle dynamics and black holes. The other feature is that if you take a charged black hole, I told you the entropy was proportional to the area, but for a charged black hole, the area remains finite as Hawking's temperature goes to 0. Roughly speaking, there's a ground state, and there's an exact balance between the gravitational attraction from gravity and the repulsion from the electrostatic forces of the charges present. And so you get a finite area of the horizon even at 0 temperature. And therefore, there is a 0 temperature entropy for any charged black hole or even a rotating black hole. The same thing applies to rotating black holes. All right, so these are the two characteristic properties of a whole class of black holes. And, so this has a perfect match with these two properties I showed you about. And if I take what we know about this tells you something. Now we have, since we have the example of the SYK model, tells us that this Bekenstein-Hawking entropy of a charged black hole is not realized by an exponentially large ground state degeneracy. In fact, all the string theory calculations were done in supersymmetric black holes, where they do have huge degeneracy of the ground state. So now we know that that's not needed. Here's a model where you can actually see that if you don't have low energy supersymmetry, which we don't in our universe, at low temperatures, black holes need not have any degeneracy. You can still get the zero temperature entropy. Okay, so that's a curious observation that connects these two problems together and leads to some interesting conclusions. But it's much better than that today. You can actually make a quantitative connection and learn something new about black holes. So if you take, now we're going to take Einstein-Maxwell theory and try to quantize it using a Feynman path interval. Well, that's usually impossible, but for a charged black hole, it turns out you can do it. It's something that, in principle, Hawking could have worked out, but not having had the example of the SYK model, I'm theorizing, it was not so easy to see where to proceed. Okay, so what you do is you zoom in to the horizon of a charged black hole, and then it turns out you can neglect, this is a feature of Einstein's equation and the Reisner-Nordstrom solution, you can neglect all the higher angular momentum modes. So you just have one spatial direction, the radial direction to worry about, which I call zeta. So the quantum theory, you can reduce the quantum theory of Einstein and Maxwell, quantize it in one space and one time direction. Okay. Now, so that theory should describe then, by this picture I've given you, entanglement just on one point. So somehow the low energy theory of a charged black hole is about entanglement at one point on the horizon, representing the zero angular momentum mode of the charged black hole. So it's in fact, it's a good, in fact, you can prove that you can just, the equations you get from semi-classical equation from Maxwell and Einstein are exactly the equations you get by a semi-classical quantization of the SYK model in the large N limit. Okay, so this is reviewed in this review article, but I'm not responsible for any of this. Maldacena and Stanford and Kitaev played an important role in this remarkable connection between, you can derive the same theory from the SYK model or from the Einstein-Maxwell equation. So this has led to some advances in answering the basic question, what is the density of states of a charged black hole? And this is the answer. So here, which owes a lot to the developments on the SYK model. But in the end, like many of these things, you could have gotten this without ever knowing about the SYK model. But having a solvable example finally showed the way to proceed. So at no stage in this calculation do you explicitly have to refer to the SYK model, but it gave the signposts and what you have to do. And it was only done after the analysis calculation with the SYK model. So this is the Bekenstein-Hawking factor. This cinch I showed you earlier, you can now get the precise coefficient, gives you the envelope of these states. And then there's a prefactor that's a bit beyond the SYK model. It was worked out by Ilyasu Mursi and Turiachi just a couple of years ago. All right, so that's a totally unexpected gift as far as I'm concerned, where this silly little model we were studying suddenly turned out to be what was needed to make some real progress in the theory of quantum black holes. So, well, what about the original problem that motivated us? I've already told you we can't possibly apply it to the cuprates directly, because you do get the right Planckian time, but you don't get the right entropy, and many other things don't work out. So anyway, so this is something many people have been thinking about a lot in the last 10 years or so. And so you want to start from everything we've learned about the SYK model, thanks to the string theorists, and see if we can now modify in a way that actually makes progress on the theory of strange matter. So I have about 5 minutes left, Tomo. Can I take 5 more minutes? Not really? Okay. I'll speak fast. Okay, thank you. So I'll tell you about one particular direction we have taken very quickly, especially work led by Avishkar Patel, who's a postdoc here in New York at the Flatiron Institute. All right, so we want to understand this strange metal. So we'll take a point of view that actually goes back quite a while, that we think of the strange metal as some intermediate region between these two phases. there's some kind of quantum phase transition between these two phases, and it's something to do with the nature of that transition. So this is the kind of phase diagram you would draw. We have some parameter that you're varying, and then there's some scalar field, which when it condenses gives you the other kind of metallic state. So this is something that Andy Millis has played a fundamental role in developing. And so if you take some spin density wave order parameter related to the antiferromagnetism, you can get some of the physics that's present in the strange metal. This is something there's been a lot of progress on recently after accounting for the disorder. But we know from experiments that this kind of spin density wave order is not really present at the higher temperatures where you see the spin density wave order. So what do you need there? So there, I believe we need a more complicated type of phase transition, which is rather similar, where you get this spin liquid background I mentioned for the pseudogap. So you need a transition from something without a spin liquid to something with a spin liquid in the background, and look at how it reacts to, in fact, very crucially, this has been the key to the recent progress, to include spatial disorder in the position of the quantum critical point, which is always present in any real material. So just to give you a very simple picture of how this could happen, how you could get a change in the volume of the Fermi surface without any broken symmetry. So you can imagine that you have, a two-band system called a Kondo lattice. You don't have that in the cuprates, but let me just allow me that simplification. So one band forms a spin liquid, like Anderson spin liquid, and the other band forms a Fermi surface. And now you turn up the coupling between them. It turns out you need a finite coupling before which the so-called Kondo effect takes over. And basically, these spins, rather than forming similar to each other, try to screen the electron, the other way around. The electrons tend to screen the spins in the so-called Kondo screening cloud. And that leads to what's called a large Fermi surface, where it counts all the electrons. And this is where the Luttinger rule applies, whereas here, you violated the Luttinger rule, but you have a spin liquid around. Okay, so if you want to look at the theory of this transition, which is, you can write down some field theory, where you have the spin-ons and the electrons, they couple to this Higgs boson, which converts a spin-on to an electron, and you write down some Landau-Ginzburg action for the rest of the fluctuation. So this is the canonical Hertz-Millis procedure. But then now you put in blue some disorder. Now the usual way you put in disorder is in elastic scattering of the electrons. And those effects are relatively weak. Turns out the most important effect is a fluctuation in the local position of the critical point. All right, so this kind of model is also around for a while. And what we realized more recently is that the more efficient way to treat this, inspired by all the SYK tricks, is to move this disorder from here to the coupling. And you can do that, at least in the simple model, simply by rescaling phi. So there's a long story about when this works and when this doesn't work, which I'm happy to tell you about in private. So you get a model like this, where you have a random coupling. All right, so now you just go to town with all the tricks you learned from SYK, which was the whole reason for existence of SYK was the random interaction. And we learned how to treat it in a certain approximation, which became exact in the large N limit. And all of those things we now apply here. So here again, all of this could have been done 20 years ago. It's just that there wasn't a simple example that showed us this is the way you should go. Anyway, so when you do this, you can in fact reproduce pretty much the experimental data for the optical conductivity, and even the key thing, the entropy works out, right? It looks like T log T, which is roughly consistent with experiments. Anyway, so that's very much work in progress, but we're very excited how we seem to be getting qualitatively similar results from a relatively simple model. And there are also tests of this in some very beautiful Monte Carlo simulations by Avishkar Patel and others. Okay, so let me conclude. So I've told you about two different types of entanglement. entanglement of stationary particles, where they just entangle some quantum number like spin or whether they're in the ground state or the Rydberg state. And so you can get interesting gap Z2 spin liquids from that. For the pseudogap, I believe to understand this kind of spectrum, there's a background of a different spin liquid, which is actually gapless and seems to appear on the square lattice. And then we talked about entanglement of mobile electrons. And there's the solvable model of mobile electrons, which is the SYK model, which has no quasi-particle-like excitations. And some generalization of this to two dimensions yields a strange metal, which has many of the characteristics of observation. The other nice thing about it, I think, is it's a very general model in the end. It applies to many different quantum phase transitions. And so it gives a route to understanding why the same strange metal is seen in so many different materials with very different microscopics. And then, amazingly, this toy model turned out to be, you don't have to modify it at all. You take the toy model and it is exactly what's needed to make progress in understanding the density of states and many other properties of charge and rotating black holes. Thank you.
The questions from the article pieces from article pieces. Or
Can I ask an obnoxious question?
Please.
Because it's really a question directed at experimentalists. You showed the certain broadness in neutron scattering.
Yes, okay.
Which was a kind of indirect evidence for interesting things.
Yes.
Is there a more direct experimental approach that I could apply to know if there was interesting things? That's the obnoxious question.
Fair enough. Yeah, we've been thinking about that. I mean, I think I have hope that in something like in the cold atom experiment. So there is, these very beautiful experiments by the Greiner group and also Emmanuel Bloch, also the Hubbard model on fairly large systems. And they have been measuring various multi-point correlation functions between the spins and the holes. And I think what I would be nice to do is for them to do some dynamic experiments on the local scale. And I think that can give, so in one dimension, that has led to fairly direct evidence for spin-ons. And I think this is something I hope they can do. So I'm optimistic that he'll be one quantum device which will actually teach us something new.
any other question? No? Yes,
Yeah.
you are saying that this what did Kitaev? What did he do?
Oh,
And
sorry.
how did you get acquainted with him? How he is in
Yeah, my life has intersected Kitaev in both stories, as you may have noticed. There was the Z2 spin liquid, then became the Kitaev toric code. So the model I showed you is, in fact, the form that Kitaev wrote it down. It's not the form that we were working in. We were working in terms of spins, and that required a more complicated larger limit. So this particular model is really in the form written by Kitaev, but it has this. The solution is exactly the same as the model we wrote on. It's a bit more complicated. It has another flavor associated with it, because we were, in a sense, trying to be physical. We were trying to take something at least somewhat related to the real world. Kitaev was freer in his thinking, and then the real world followed. So.
Okay, so good thing to speak again for very nice. We'll be available from 3:30 to 4:30, or especially for graduate students and postdocs for the coffee hour today. If you'd like to, talk with Bill, please come for the coffee hour.